In this session, we're going to talk about interval estimation. And interval estimation is actually our first step into inferential statistics, which is the real reason you have to take the course. It allows us to make a good estimate of the population parameters based on the sample. So just to review, the last topic that we were looking at was sampling distributions. And in sampling distributions, we knew what the population mean was. And what we were trying to do is we were trying to find the probability of getting a sample mean close to the population mean. What's going to be different today is that we're not going to know what the population mean is, but we're going to want to estimate it. So what we're going to start off by doing is taking a sample and getting our sample mean. And that sample mean is our one best guess for what the population mean is. And we call that one best guess a point estimate. And one of the things we know about that one best guess is that it's probably wrong. So to increase the chance that we really have the population mean, what we're going to do is we're going to build an interval around this. So we're going to go up a bit and we're going to go down a bit. And that distance that we travel, unlike my diagram, is the same in either direction. And we give that distance the notation, the big giant E. And the big giant E actually stands for margin of error. And the margin of error is basically made up of three different things. The first component is how sure we want to be. So the more sure we want to be that we've got the population mean somewhere in our estimate, the wider we're going to have to make that margin of error. The second component is the standard deviation. So we start with the standard deviation and we'll adjust it for the sample size, just like we did in sampling distributions. What's a little bit unrealistic in this first example is that we're going to assume that even though we don't know what the population mean mu is, we know what the population standard deviation sigma is. So what we're going to assume for this lesson anyway is that we know what sigma is. And the final piece of the margin of error is the sample size. So the larger the sample size, the more sure we are. And let's go have a look at an example and we'll see how all these things fit together. So here's our example. A local political party is concerned about housing affordability. Having done nothing for 4 years, they do not want to act in haste. They commission a study on the amount of first mortgages taken in the Vancouver area. A sample of 36 transactions has a mean mortgage amount of $625,000 and a standard deviation of $150,000. And what we're going to assume is that this value is sigma. And the question is, find the 95% confidence interval for the true mean first mortgage amount. So what happens here is we're starting off with our X bar, which is 625,000. Now we realize that's probably wrong. So what we're going to do is we're going to build an interval around it. So we're going to go up a little bit and we're going to go down a little bit. And when we do that, we're going to wind up with a 95% chance that somewhere in this interval, maybe there, maybe over here, we're going to have the real population mean. So this margin of error, the way we calculate it, is that first component is how sure do we want to be? Well, we have this way of figuring out probability, and what we're going to use is a z-stat. The alpha over 2, from here on in, when we talk about alpha in statistics, what we're going to talk about is the amount of uncertainty. Now, we don't actually use the alpha over 2 in the calculation. It's just a notation that will help us get to the right z-score. We're going to take that and multiply it by sigma, the standard deviation, and we'll divide the whole mess by the square root of n. Now in this case, we don't have to worry about the population being normally distributed because n is 36, and remember from the central limit theory, as long as our sample size is bigger than 30, we can assume the distribution of sample means is normally distributed. So let's look at our Z-stat first. So we want to be 95% sure. So what that means is the 95% is going to be split symmetrically around the mean. What that means is our alpha, the amount of uncertainty that we're willing to live with, is 5%, and half of that alpha, alpha over 2, or 0.025, is going to get put into each tail. So to be 95% sure, we need to find these Z-scores. So what we're going to do is go to our standard normal table and look at 0.025, which will give us the lower tail, and then by symmetry, we can find the upper tail. So 0.025, and there it is, right there. So we actually have 0.025, and that corresponds to a Z-score of minus 1.96. So that means our negative Z-score is going to be minus 1.96, and our positive Z-score by symmetry is going to be plus 1.96. So if we go back up and look at our formula that's forming, we now know that our Z-score is 1.96. Don't say, what about the negative 1.96? When we get our margin of error, we can add it and subtract it to the sample mean. So right now, our standard deviation from the problem is 150,000. And our sample size is 36. We want the square root of 36. So let's work this out. 150,000, and the square root of 36 is 6. 150,000 divided by 6 is 25,000. 1.96 times 25,000 comes out to a freakishly nice $49,000. So that's our margin of error. Now to get our interval, we're going to start off with our mean of 625,000. And to that mean, we're going to add a margin of error. And when we do that, that's going to give us 674,000. And we're going to subtract a margin of error. And when we do that, that's going to give us 576,000. So our interval estimate is somewhere between 576,000 and 674,000. Now, another important transition that we make starting in this section is notation, and the way you set up your answers becomes more important even than the calculation. So to set up a proper interval estimation answer, what we need to do is we need to say three things. The first thing we need is we need a probability statement. So the way that we would deal with that for this question is we'd say that the 95% confidence interval for the second part of your answer has to say something about the true population mean, and what we're really saying is the population parameter. So the way we would say this is the 95% confidence interval for the true population mean dollar value of a first mortgage is. And finally, when we do that, we can write our interval. Okay, now the easiest way to write the interval, I think, is to put the mean in the middle, put your upper boundary, and our upper boundary, it was 674,000. And our lower boundary was 576,000. So notice the direction of the inequality signs. What we're saying is that our mean is between 576,000 and 474,000. And to be doubly sure that I said population parameter, I said it in words, true population mean, and I put the symbol down, mu. So we're covered. Okay, there were three parts to this question, but really the second part, the only thing that is going to change is that instead of having 95% certainty, we have 90% certainty. which means 5% in each tail. So our z-score would be 1.645. So let's just jump ahead and have a look at the last part of this calculation. And the last part of this calculation is finding the sample size. So C says they would like to reduce the margin of error on the 95% interval to no more than 30,000. How large a sample should they use? So the no more than 30,000 we'll talk about, but it gives us a convention that we have to use when finding sample size. So it's really just an exercise in algebra. In this case, we'll just write down our formula. E is equal to Z alpha over 2 times sigma, all divided by the square root of n. We'll rearrange this because we don't want to solve for E, we want to solve for n. So if we rearrange this, what we get is the square root of n is equal to Z alpha over 2 times sigma, all divided by the margin of error E. Now we don't want the square root of n, we just want plain old n, so we'll square both sides and that'll give us the formula n is equal to Z alpha over 2 times sigma, all divided by E, all squared. Okay, so let's plug in numbers and see what we get. N is equal to, we already figured out that our z-score is 1.96. Our sigma is 150,000. And our margin of error is going to be 30,000. So 1.96 times 150,000 divided by 30,000. It's going to give us 9.8. 9.8 squared gives us 96.04. Now what we were answering is how many people we actually need to sample, so that number can't be a fraction. Now the assumption that we make when we do these problems is that people gave us this $30,000 number for a reason, and if they want a margin of error of 30,000, what they're really saying is 30,000 is the absolute maximum margin of error we're willing to live with. We want you to come in at $30,000 or less. So because of that, what we're going to have to do is always round up your sample size. So we can't sample 0.04 of a person, and because we want to make a margin of error of no more than 30,000, we have to round this up, and we'd have to sample 97 transactions. Now, what I'm really trying to say about this is this. In an Excel spreadsheet, I've put all the calculations. So here's our margin of error. Our margin of error comes out to be exactly $30,000 if we have a sample size of 96.04. What happens if we round it down and use normal rules of rounding? Well, if we do that, our margin of error goes up to $30,006, and the people that wanted a margin of error of no more than $30,000 yell and scream at us, and at worst, we might have to do the whole study again. Okay, that's the first part. We will have 2 more lessons on this section.